The energy system is undergoing a remarkable transformation. Oil and gas companies are pivoting their investments toward lower carbon energy solutions. And this shift is not just a trend, it's a blueprint for scaling hydrogen technologies. For hydrogen engineers, this is an exciting time filled with opportunities and challenges. For over a century, the oil and gas sector has built a robust foundation in subsurface science and process engineering. Now, these capabilities are being repurposed to support the energy transition. While companies continue to transport molecules, the focus is on reducing the carbon intensity of these molecules. This evolution has led to a diverse energy portfolio where wind and solar power electrolyzers, carbon capture technologies support hard-to-abate processes, and hydrogen serves as a vital link between power generation, industry, and mobility. Investment in renewable energy is surging, with capital flowing into wind, solar, hydro, and advanced biofuels. Integrated energy companies are leveraging their expertise in load profiles and interconnection risks. Offshore wind, for instance, benefits from decades of marine construction experience, which directly impacts hydrogen production. The result? Cheaper, more reliable renewable energy leads to lower costs for green hydrogen. As hydrogen engineers, our focus has expanded from merely improving stack efficiency to designing entire systems that optimize power electronics, heat integration, and water management. Carbon capture, utilization, and storage, CCUS, play a crucial role in this transition. It serves as a bridge to decarbonize existing processes and anchors blue hydrogen production. The technology behind carbon capture is familiar to us. It involves solvent regeneration, heat integration, and uptime economics similar to gas processing. By integrating CCUS, we can reduce the carbon intensity of hydrogen production while also gaining valuable experience in leak detection and pressure management, which are essential for hydrogen pipelines. Hydrogen production itself is evolving. The refining industry has a long history of hydrogen production, and now the focus is on cutting carbon intensity and expanding its applications. Blue hydrogen utilizes large-scale steam methane reforming with integrated carbon capture, while green hydrogen relies on electrolysis, powered by renewable energy. This shift requires us to consider system-level performance, including stack ramping under variable power and efficient water logistics. Digital transformation is another key aspect of this evolution. Advanced control systems are being enhanced with continuous emissions measurement and predictive analytics. In carbon capture units, soft sensors help optimize performance, while in electrolyzers, digital twins predict stack aging. This level of digital integration not only improves efficiency, but also ensures compliance with increasingly stringent emissions reporting requirements. Collaboration is essential in this complex landscape. No megaproject succeeds in isolation. Governments, industrial customers, and communities all play vital roles. Cross-sector partnerships are emerging, linking renewable developers, electrolyzer manufacturers, and end users. For hydrogen engineers, this means designing systems with interoperability in mind and embracing certification as a project accelerator. However, we face real challenges. Capital remains constrained, and supply chains for critical components, like high-pressure vessels and hydrogen-compatible valves, are still developing. The physics of hydrogen presents unique challenges, from low energy density to embrittlement issues in materials. Yet, with these challenges come opportunities. As renewable energy costs continue to decline, blue hydrogen can leverage existing assets to deliver early volumes, and industrial clusters can optimize operations in ways that standalone plants cannot. As hydrogen engineers, our roles are becoming both specialized and integrative. We must design process trains that withstand dynamic operations, select materials that resist embrittlement, and ensure that our systems are efficient and safe. We need to balance throughput and margin while adhering to rigorous safety standards. The transition to a low-carbon energy system is not linear, but it is decisive. By focusing on rigorous design, data-driven performance, and safety, hydrogen can become a cornerstone of a resilient energy future.